to talk about electric fields for just a few minutes today. I had some notes out there regarding an introduction to electrostatic and electrostatic forces. I have some videos out there regarding the fundamentals of a circuit and circuit analysis. I don't have anything that's talking about the electric field and how that kind of relates to a circuit. So that's the goal for today. We know if we have a positive charge that is fixed and cannot move, and if we put a small positive test charge near it, it's going to be repelled because like charges repel one another. And so this positive charge is going to want to move directly away from it. And it doesn't matter where the charge is around it, it's going to want to move directly away from the positive charge. And so these green lines represent what is known as the electric field. The electric field for a positive charge points directly away from it in all directions. The electric field is basically the direction a positive test charge wants to move when there's that electrostatic repelling force on it. Okay. Next situation. We have a large negative charge that is fixed in place. If I have a positive test charge that's near it, it's going to want to be attracted to that negative charge because opposites attract. And you can probably guess that no matter where I put that positive test charge, it's going to be attracted to the negative charge. And so the green arrows define the electric field around a negative charge. So here's my electric field around the positive charge. So the electric field points away from the positive and towards the negative. Okay. Now, let's put everything together a little bit. Let's say we have a positive charge, does not move. Let's say we have a negative charge, does not move. And if I put that positive test charge directly in between them, it's going to be pushed away from the positive, pulled towards the negative, so it's going to take a path just like that. Fair enough. Let's say the positive test charge is down here. It's going to feel a big repulsion from the positive directly out from the positive. However, it's also going to feel a little bit of an attractive force towards the negative. It's kind of far away from the negative, so that attracting force is going to be a lot less than the repelling force. The net force added on that charge is going to be someplace like that. So it's not directly away from the positive, and it's not directly towards the negative. As that test charge gets down here, it's going to feel less of a repulsion from the positive, more of an attraction to the negative, and the direction of the force is going to be more turned towards the negative. And in effect, what it's going to happen is the path it's going to take is going to curve around from positive to negative. These electric field lines are the paths that a positive test charge will take to get from the positive to the negative. And so if it goes out on the opposite side of the positive, it's going to go all the way around and come into the negative. Big old loop. So this is the path the test charge will take to get to the negative. The test charge only has one path. Depending upon where it is, there's only one possible path. So these field lines do not cross. There's a lot more into why they don't cross, which I'm not going to get into. Just understand that they don't cross, and it takes this path. Next situation. Similar situation. We have a positive test charge there. That's a pretty nice circle. We have a negative there. That might even be a better circle. And I'm going to put my test charge right there, my positive Q test charge. The amount of energy it has in this electric field is referred to as electric potential energy. The electric potential energy is the amount of energy that the charge has. The electric potential energy is measured in volts. So when the charge is in, let's say, position number 1, it has a certain voltage, and let's call that V1. Think about, for a second, gravitational potential energy. We have the Earth. We have some object 10 meters up in the air. It's got gravitational potential energy based on mgh. As the object falls, the gravitational potential energy is going to decrease because it's being pulled towards the Earth. The same idea is taking place here with the test charge. It has a certain amount of electric potential energy, V1. As the test charge moves and is being pulled by force towards the negative charge, its electric potential energy is going to decrease. And when we get to position 2, it might have a voltage 2. Now in this case, our voltage at position 2 is less than our voltage at position 1. Because it's getting closer to the negative charge, its electric potential energy is going to decrease. I'm not going to get into the math as to why that is. That's more of a Physics C issue. Just understand that as this positive charge comes towards the negative charge, its electric potential energy is going to decrease. The thing about the whole situation is that the actual value of V1 and V2 don't really matter. What matters is the difference in V, which is V2 minus V1, the change in electric potential energy. The change in electric potential energy, that delta V, is what we commonly call simply voltage. For example, when the outlet in a house is 120 volts, that 120 is actually the change in voltage between the two prongs. It's actually a change in voltage. We just simply refer to it as voltage. In the Physics 1, when we talk about voltage, in reality, we're talking about change in electric potential energy, or delta V. Potential difference is another way of referring to that. We're not going to talk about the voltage associated with the charge in the electric field. That's for a different course. That's for the Physicks C E&M. Just be careful about that terminology. If we're talking about a battery, if you consider one of those 9-volt batteries, then what that really means is between the positive to the negative, the change in voltage is 9 volts. So when the charge is right there, it might have 9 volts of electric potential energy. When it's right there, it has, for all practical purposes, 0 volts. So our change in voltage is 9 volts. That's the idea behind a battery. The reason a battery has a positive and a negative terminal is that the positive provides our plus charge, the negative provides our negative charge, and between those two terminals, when the circuit is set up, we have a closed loop, and we can establish an electric field throughout that loop. That's what causes the charge to move. Let me illustrate that. Give me a second to sketch it up. We have a 9-volt battery. We're going to take some wires and connect it to a light bulb. So, when we complete the circuit and we have that a complete wire from the positive to negative, we establish an electric field in the wire. As soon as that electric field is established, the charge starts to move. And when that charge starts moving, that's what gives us electricity. So electric field in the wire causes charge to move. The charge moves everywhere. All the charge throughout the line is moving instantaneously. It's not like it's moving it's not like we have a charge from the positive terminal that's then going down through here. All the charge collectively is moving together throughout the entire wire. All right, I think that's all I really wanted to kind of go over today. That gets into the fundamental basics between tying electrostatic force into the electric field, into a circuit, and how all those things work together. This is information-wise partway between AP Physics 1 and AP Physics C E&M. A little bit more than what the Physics 1 needs to know. It does not get into all the details that you cover in E&M, but I think it is intended to bridge the gap in the AP Physics 1 between electrostatic force and circuits, since we don't cover electric fields. All right, that's all I have for you today. Hope this was of some value. Good luck.